So, welcome back to the next module of surface characterization. In last module we talked about FTIR in ATR mode, where we tried to look at the surface characterization. Now, I am coming to a technique which is not really a surface characterization technique, but is very useful, and at times it can detect materials at low concentrations also, and they are very specific to certain kind of changes. So, I will not call it a surface characterization technique, but it is used a lot nowadays in nano modification, in nanomaterials, in application of nanomaterials. So, that is why I have kept this technique, and one can judiciously look at this technique of Raman spectroscopy even to look at the surfaces or very small concentrations. Though I will not be covering that in too much detail, because those are very specific type of experiments which are difficult to perform in the normal lab setup, but I will give you certain information on that aspect as well. So, let us start in this module about Raman spectroscopy. As you know, Raman comes spectroscopy comes from C.V. Raman effect, which is for which he got a Nobel Prize, and based on this there is a spectroscopy which has been developed. Now, Raman spectroscopy and IR spectroscopy are brother and sisters. I mean, they are complementary to each other in a manner, and I will explain you with time how that happens. As there is a selection rule for IR spectroscopy, that the frequency of the bond vibration must match the frequency of IR in such a manner that there should be a change in dipole. So, the dipole moment of the molecule or the bond should change when there is a vibration, and then only the IR can get absorbed, that is the IR selection rule. In this we have a slightly more rigid rule, that is not only the material should have a dipole, the polarizability of dipole. So, a material will create a dipole only if it can polarize. That means, the electrons can separate, the cloud of electron can move to from one atom to another atom, then the molecule has polarized under a field. So, if a molecule is it is possible for a molecule to polarize under electric field, then that is the first requirement for the material to be active for Raman, but that is not enough. The polarization itself is happening because of polarizability, that means the ability of the molecule to polarize. This polarizability, that is the ability, that itself should change when we when the molecule is vibrating. So, let us come to the slide, let me put it again in a better way. So, polarizability of a molecule, which is the ability of electrons in a bond to move under an external electric field. This polarizability, which is the ability of electrons in a bond to move under an external field, that itself should change. This polarizability, this ability should change. How should it change? When the bond vibrates. So, if a bond is vibrating and with vibration the polarizability of that bond is changing, then it is Raman active. So, if the polarizability does not change with the vibration, then it is not active in Raman. So, if polarizability changes significantly, then it is Raman. Why I am saying it is significant change? Because small changes will be weak Raman active, and that you may not be able to receive. And why the signals are weak, we will come to that in the next slide, or maybe slides subsequent to that. So, let us go to the next slide and see more information. So, what happens, as I will explain you in the future slides also in a more diagrammatic manner, that Raman's signals are actually very weak. They get created in a very small manner. If we have a beam coming, a light beam coming, if you have a light beam coming, then a very small amount of light which is impacted on the sample gets converted into a Raman signal. So, we cannot use a simple light source. For this we have to really use an intense laser, a very strong, bright, coherent laser we have to use, light source we have to use, and then we can get some Raman signal, some amount of Raman signal which will be useful for detection. So, therefore, if a molecule is weakly Raman active, then even after using a strong laser light, we will not be able to detect the signal. So, therefore, either the molecule has to be significantly Raman active, or we have to have a high concentration, a very strong laser beam. So, first requirement, go to the slide, that we have to use a laser which is very strong, and we can use a visible light or a near infrared kind of lasers for that. There are many lasers which are possible, and we have to have many lasers in a Raman spectrometer, because in some wavelengths a molecule may fluorescence or it may emit light, and it may really mask the spectra. So, we have to look at which wavelength will give us a better spectra. So, usually 414 or 785 nanometer kind of lasers are used, and then as I said you before, that the change in polarizability should happen. So, if the molecule on vibration is changing its polarizability, then it converts part of the laser light. Now, this is very important part, very small part, very small part of the laser light will get converted into either a slightly higher wave number or slightly lower wave number, and I will show you this in a diagram. These are called anti-Stokes and Stokes radiations for Raman. Anti-Stokes for higher, slightly higher wave numbers, and Stokes for slightly lower wave numbers. So, if you have say 514 as the laser, then either the laser signal which will get converted into a Raman signal, it will be more than 514, that is slightly higher wave numbers, or less than 514 for slightly lower wave numbers. So, obviously, I am using it slightly wrong, please do not take me literally. 514 nanometer is the wave length, and I am here talking about wave number. So, it is the inverse, it is going to be inverse of it. So, higher wave number, slightly higher wave number means less than 514 nanometers. So, let me correct myself, it is less than 514 nanometers, and slightly lower wave numbers means the wavelength is slightly higher than 514 nanometer. If we use say for example 785 nanometer laser, if we use a different laser, then again it will get converted to either slightly higher or slightly lower wavelength, depending on whether it is a anti-Stokes or Stokes kind of a signal. So, this shift, these shifts in wave numbers, that is interestingly function of the chemical groups present in the molecule. So, this is something which is important. So, if there is a shift, this shift, how much shift will be there, how many wave numbers the shift will take place, that depends on what kind of bond is present in the molecule. So, as in IR, the IR was getting absorbed by a particular bond because it has a particular frequency. Here also, because this bond has a particular frequency, the shift will be according to that frequency. So, we can detect, if we can detect the shift, then we can actually detect the chemical bond, and if we can do that, then we have done our job of chemical analysis. So, let us look at it in slightly more detail. So, this is how the Raman spectroscope layout is. So, you have a sample which is shown here, let me take a pointer. So, we have a sample here, and on this sample, as I told you, we need a very strong laser light, a very focused beam which comes onto the sample. As it strikes the sample, obviously it will penetrate also inside the sample to some extent, but most of it will happen from the top surface. So, that is why the changes on the surface will also get detected very easily, but it is not just only surface will be seen, it will also see the inside of the sample. And then the sample will absorb this laser light and it will re-emit it as a scattered light. Now, the scattering can be of two types, as you know, it can be a elastic scattering or it can be a inelastic scattering. In elastic scattering, whatever laser light or whatever wave number light was put on the sample absorbs that light and it emits that light also of the same wavelength. So, that is called elastic scattering, that means nothing was lost. the energy, same energy got absorbed and emitted. However, in inelastic scattering, that light which gets absorbed, what gets emitted is slightly different from what gets absorbed. So, that is inelastic. So, let us come back to the graph. So, this sample will actually scatter both kinds of wavelengths, one which is of the laser itself, which is red, shown in red here. These are elastic scatterings, or it can also scatter part of it. I have shown only one light coming, although there will be many such lights coming, which will be inelastic scattering, part of inelastic scattering, and that is the Raman signal actually which we are looking for. So, what we do is we put a filter, and we reject all these red lights which are coming from laser dispersion. So, we reject those by putting a filter, narrow filter, say this is 514, then we put a filter. Let me take a pen and write to you. So, we take if this is 514 nanometer laser, then what we will do is we will put a filter also of 514 nanometer, so that this lights get rejected, and what passes through is a Raman signal, and this is taken by the spectroscometer, and the spectrometer starts to capture the signal. So, very simple, very straightforward. So, what happens? What is happening in the sample? Let us look at inside the sample what is happening. These are the energy levels in a chemical compound. The lower ones are called the filled orbitals, and the upper ones are called the anti bonding or say unfilled orbitals. So, these splits which I have shown here to you are levels created by a vibration. So, when a vibration happens, then obviously the energy levels of the molecule changes from 1 to 2 with a very small number, and in IR if you look at, we are looking at the absorptions in these energy states, from a low energy state to a higher energy state as the bond stretches or as the bond bends or as the bond waves. So, this is the IR absorption which happens, and that was the absorption. But in this case what is happening is we have put a light which is strong laser light. So, it takes the electrons from the ground state to the excited state, and the same are recovered back. So, you get a light out. So, let me select a pen. So, you get a light out which is of the same wavelength. So, light comes, it gets absorbed, and as it emits out, as it comes to the ground level, it emits out at the same wavelength, nothing has changed. But what happens in an inelastic scattering, that whatever light takes an absorption to excited state, when it comes back, it does not come back to the same vibration level, it comes to a different vibration level. That can happen because my molecule is vibrating, the atom is vibrating, the bond is vibrating. So, what happens is then what you get is slightly less energy which is coming out. So, this is same, but here it is lower, or what may happen is it may absorb light from a slightly higher vibration state to a higher vibration, and what comes back, it actually comes back to the ground level of vibration. So, here the light emitted is of higher energy. Higher energy means higher wave numbers and lower means lower wave numbers, then compared to the light which we have put. So, it does not matter what light we put in a Raman spectroscopy, what matters is how much it got shifted, and as you can see from the diagram again, that gets shifted by one vibration level. One vibration level means it can actually detect that bond vibration. So, this is what we are looking at. Let us come to the next slide and look at it at the spectra. So, the spectra what we get, obviously what we are blocking is Rayleigh scattering, which is the laser light which was red in our case. So, let me make it red so that we do not confuse. So, this is the red, and we have put a filter. So, this filter is actually blocking this intense scattering, which is elastic scattering, and the rest of it is either Stokes-Raman scattering or an anti-Stokes-Raman scattering. So, either the wavelength number is decreasing or the wavelength number is increasing, wave number, either the wave numbers are decreasing or the wave numbers are increasing. So, we do not really look at the entire spectra. What we do is we actually divide this and we reject this, the anti-Stokes, and what we plot is only the Stokes-Raman. So, our y axis is scattered intensity, our x axis is Stokes-Raman intensities, wave numbers. So, what you can see here is a shift, a change from the main peak of another peak. So, these are called shifts, these are wave number shifts, and these wave number shifts are actually characteristic of the vibration of that molecule. So, in IR we had only absorption at the wave numbers which were the characteristic peaks or characteristic energies of the bond vibration. Here the shifts are of those characteristic wave numbers. So, if you look at the positions at which the IR happens for certain bonds, the Raman will also happen at those same wave number shifts. So, it is very easy to interpret a Raman spectrum, but what is very interesting is that the bonds vibration, the bond vibrations which are absorbable by or detectable by IR actually are not active in Raman, and the bond vibrations which are active in Raman are usually not so active in IR. So, it is a complementary technique. That means, some of the vibrations which you can detect by IR you cannot detect by Raman, but those which you cannot detect in IR you can detect by Raman. So, both are complementary, and in some cases complementary techniques work very well, especially when you have a lot of moisture, your reaction is going on in water or your sample has lot of water and it is not suitable for IR, or there are bond vibrations which you are looking at which are not available in IR. So, you can actually find them in Raman. So, let us go to the next slide and look at this is just so let us look at how they are complementary. So, this is a spectra is one example of a carbon dioxide, and the center blue circle or sphere is the carbon and two red spheres are the oxygen. So, this is how a CO2 molecule is, right. So, this is carbon and this is oxygen and this is also oxygen, carbon, oxygen, oxygen. Now, you can look at here, this is a asymmetric stretching, one bond is extending, the other is contracting, right. Here this is bending, the molecules are the center part is going up and down, which means the two other ends are going either down or in the opposite end. So, this is bending. In both these cases you will see that the dipole is actually oscillating, because as the bonds distances change the electrons move, and here also the electrons move because the electronegative and electropositive atoms they displace with time. So, they are IR active. However, in Raman this is symmetric stretching. So, you have carbon and two oxygen, both are symmetrically, they are stretching at the same time, contracted at the same time. So, if you look at the dipole, its dipole is not changing because it is stable, it is not oscillating, right. Here it is oscillating, here it is actually oscillating, here it is not oscillating. So, this is not IR active, but it is Raman active. Why? Because as the bond changes, the polarizability changes, and since polarizability changes, and this material becomes, or this bond vibration becomes a Raman active material. So, it is a symmetric stretching. As a general thumb rule, symmetric stretchings are Raman active and asymmetric stretchings and bendings are usually infrared active. So, we are coming to the end of this module as well, and I just want to remind you that this material actually, or this technique can be used for finding various chemical elements which are present, that is bonds which are present or functional groups which are present in a molecule, and it can also talk about the interaction between the two molecules. So, I will give you now an example how a Raman can be very effectively used to look at the interaction. If you mix two materials, if you coat one material over the other material or just blend them in some proportion, then you can actually look at the interactions, and these interactions can show up very well. So, this is an example which we published a couple of years back. Let us come to the slide. It is the Raman of DMF. Let me select a highlighter here. So, we have DMF which is a solvent, and then we have Raman of another sample where PAN, which is polyacrylonitrile polymer dissolved in DMF, dimethyl formamide, and then we have another solution which has ZNO, zinc oxide nanoparticles, PAN, which is the polymer, and the solvent, these three things together. So, the spectra here, what you see here, one is of DMF. So, this is the black line, this black thing is DMF, and you see it has a characteristic. So, we are only looking at one region, one peak. Obviously, the spectra is very large. So, I am just looking at one peak. So, at around 1660 we had a peak for DMF, and when we added PAN to this peak to this solvent, then what happens, this peak shifts to slightly more than 1660, actually it was 1665, now it has gone to 1675. So, this has shifted, and then when I go further and add zinc oxide in it now, then what happens, this peak shifts further. Now, this peak has gone to almost 1685, almost 1690 approximately. So, what has happened? Actually, the CO bond. So, we are looking at actually CO bond, carbonyl bond, C and C triple bond N of PAN with DMF, and also of ZNO, and ZNO has OH groups and they interact with CO bond. So, we are looking at this. So, just looking at the various interaction, one can see that the peak shifts, which means the interaction is very strong, and one can say that when we are adding materials, what kind of interaction, what kind of groups are involved in these kinds of mixtures which we prepare, or these kind of modifications which we prepare. So, this is I am coming to now the end of this module. So, just to remind you again, the importance is of the Raman is it is not affected by water. You can actually do reaction inside of water and monitor the growth of reaction. You can also look at the material or the textile which is heavily loaded with water and the changes have taken place. You also, another interesting thing is, unlike IR, you can use glass. Raman is transparent to glass, because it happens in a visible region. So, it's transparent to glass. So, you can use a microscope. So, if you use a microscope, then it becomes a micro Raman, and you can really pinpoint a laser to a very small part of the sample. That means 50 microns or 10 microns kind of a radius, and you can look at the changes, chemical changes at that spot, and then you can change that spot from one position to another position to another position. So, you can focus the light at different parts of the material. So, you take a laser, you can focus it on the surface and see what is the surface, then you can go inside, see what is inside of the surface, and if there are multiple layers inside the sample, you can look at each and every layer inside the sample and see how they function, because a microscope can actually focus the light inside or outside the sample depending on where you want. Obviously, the sample has to be transparent for that. So, such kind of arrangement is called confocal micro Raman spectroscopy, and a light microscope is used for that purpose. So, let us come back to the slide again. So, what we have said is that the presence of water does not affect Raman. We can use glass, which means We can have sample on a glass or a glass tube, or it does not matter, or a glass slide. We can use a light microscope where the lenses are of glass to focus the laser light onto the sample surface, or we can actually take it inside the sample if the sample is transparent, and we can do scanning of the sample either in the depth. So, if this is my sample, so I can go inside of the sample or I can go across the sample and look at how the chemical nature of the sample is changing. So, Raman is very useful in such cases, and we can really use these instrument or this technique in particular for graphitic content in a sample versus say amorphous carbon, that is very important for carbon based nanomaterials, or for detecting metals like silver and gold. They give very strong signals actually. So, if there is a silver nanowire or a silver particle which is added inside a polymer and it is interacting, you can get very strong signals, or it is used for detecting very small amounts of biological molecules which are very Raman active, and all host of chemical compounds which can be detected by Raman. So, thank you very much. We come to the end of this module now, and I hope you have been able to learn about Raman spectroscopy, its basics and its utilization in doing surface as well as bulk analysis and interaction when you make mixtures of materials, which is very important in telling the mechanism or investigating the mechanism of a functionality which you have created on your textile material or in a material of use. Thank you very much.